Happy Thursday afternoon. It's now what, our third weekend? Always exciting. Continuing with precise definition. I'm so excited.
Serious. I mean, how much?
Well, now I know what to put on your exam. Thank you. Physics major.
I've just been trying to like go home and trying to rewrite all this stuff. With those stuff, I think make no sense. Like, if I go to my just like you go too fast.
So we assume epsilon greater than 0 is given to us. What do we want to show?
Is it there exists deltas greater than 0?
What's that what?
X minus 2. No, I would like the absolute value.
What about it?
It's less than delta.
Keep going.
Like arrow.
So if
Yeah.
the absolute value of x minus 2 is less than delta, then what?
The value of x cubed minus 1 minus 7 is less than epsilon.
Let's do object. How can that be simplified?
X cubed minus 8.
How can that be simplified?
X minus 2 cubed.
You want the absolute value of x minus 2, and then you want the absolute value of x squared plus 2x plus 4.
x cubed minus 8 is the difference of cubes. Absolute value of x minus 2 we know is less than delta. Let's add a further restriction to less than or equal to 1. With that, we're going to get x is between 1 and 3. X squared plus 2x plus 4, evaluate that at 1. Which means 7 has to serve as a lower bound for x squared plus 2x plus 4. Evaluate it now at 3 to find your upper bound. Seven's a lower bound, so is negative 19. So that absolute value would be less than or equal to 19. What we now have is the absolute value in question, x cubed minus 1 minus 7, is less than or equal to 9, or less than 19 delta. 19 delta to be less than or equal to epsilon, and for delta to be less than or equal to 1. What would our choice of delta be?
The minimum of epsilon over 19 is 1.
And so we found out delta. If you've been following along, we're going to do a really difficult one.
Would you go back?
Could I guess? I am capable of it. How long? Define a little bit. You can leave it up to me. Going to prove that the limit as x approaches 2 of 5 is 5. This is really difficult. It's not absolute value. What do we know about epsilon? No, that's nice. We're essentially done. Delta can be whatever you want it to be. Because 5 minus 5 will always be less than epsilon. So this one is interesting. We've been working with polynomials. Let's look at a trick function. Prove the limit as x approaches 0, sine of x is 0. So the absolute value of sine of x. There's an interesting property with trig. That's going to wind up being less than or equal to the absolute value of x. For small values of x, sine of x is approximately x. Also, sine of x has to be between -1 and +1. Which means for larger values of x, the absolute value of sine of x will be less than the absolute value of x. Hence, we get this inequality. Oh. And that's less than double. We would need delta to be less than or equal to epsilon. So just take delta to be epsilon. So those are epsilon delta proofs. The exception of the quiz, possibly the quiz, and maybe some proofs in the lecture. We'll never see them again. Unless you're a math major. Then you see them again. So let's change gears and finish up with limits. When you were studying calc, you looked at what's called the end behavior of a function, right? What was end behavior?
In layman's terms, it's what value the function approaches as you approach infinity as your input.
Just infinity?
Or negative infinity, that one too.
So not necessarily approaching a value per se, because the function could just increase without bound, in which case it's not approaching anything. But it's how's the function behaving as your independent variable either increase without bound, right? That'd be towards infinity, or decreasing without bound, which would be towards negative infinity. Or if you let x approach something, what is that?
That sounds like a limit.
We now look at limits at infinity.
I don't like how this one's intuitive and finding an unintuitive one. Like, are we going to look at an unintuitive one later?
No, we're going to look at the formal definition later.
Okay, all right.
This is just the intuitive definition. The values of f of x become arbitrarily close to L as x becomes sufficiently large. We say the function has a limit at infinity, and we write the limit as x approaches infinity of f of x equals L. Likewise, values of f of x become arbitrarily close to L as, or for x less than 0, as the absolute value of x becomes sufficiently large. Right, so meaning x is becoming sufficiently large in the negative direction. We say the function f has a limit at negative infinity, and we write the limit as x approaches negative infinity of f of x equals L. In either of those cases, f of x seems to level out. Level out at some value. We also say that f of x converges to that value. So believe it or not, this is actually fairly useful, especially in physics. Also in economics. Right, obviously physics, what's the long-term expectation of this particle? That's the limit as t goes to infinity. What is the long-term expected profit? That'd be a limit as x approaches infinity. Or again, time approaches infinity. How does sound waves behave as you get further and further away from the source? Again, that would now be a limit as distance approaches infinity. Talking about functions, graphs of functions. How did you define horizontal asymptote?
As your input approaches this point that isn't defined, your output approaches either positive or negative infinity.
That's a vertical asymptote.
Oh, we're doing horizontal.
How is the horizontal asymptote defined in Greek calc? You know, it's defined very loosely. It's just the end behavior, essentially. Right, if at the end your function seems to level out to some value, that's horizontal asymptote. That line is horizontal asymptote. Yeah, it's not a mathematical definition.
Okay.
If the limit as x approaches either positive or negative infinity of f of x equals L, we call the line y equals L a horizontal asymptote.
And is this the formal definition of a horizontal asymptotes? Okay.
You studied one other type of asymptote in pre-calc.
Diagonal.
Which was called what?
Well, that's I don't remember.
What is it?
Is slant.
Slant or oblique. Same kind of idea. If the function is kind of leveling out to a line, diagonal line, y equals mx plus b, then that would be a slant asymptote. I would find its slope. Why is it not showing? As you take the limit as x approaches plus or minus infinity of f of x over x. That will give you the slope of your line. And then the value of the y-intercept is the limit as x approaches plus or minus infinity of f of x minus mx. The oblique asymptote is in a special category. I stop at a line. When you calculate oblique asymptotes in pre-calc, do you remember how you did that? Specifically, it was for rational, even though you don't necessarily have to have a rational.
Yeah, I remember it being thrown in there. It came up a couple of times.
Long division.
Specifically long division.
Unless it was a linear function you're using, then you could use synthetic. But we're just going to stick with division in general. Polynomial long division. Your slant asymptote was the divisor, or not the divisor, the quotient you're left with. You ignore the remainder.
Right.
Well, what if your quotient's not linear?
Well, that makes it really funky asymptote then.
Then it wasn't a slant asymptote, and that's where you stopped. If the slope is not, or not the slope, if the quotient is not linear, it is an asymptote. Because your function's still going to behave that way for large values. In general, we call these curvilinear asymptotes. So a slant asymptote is a curvilinear asymptote, so degree 1. But you could also have a degree 2, as the case here, where the curvilinear asymptote, that function behaves as y equals x squared. The formal definition of these is really hideous. I haven't actually ever studied that. So I imagine it's a pretty high level grad topic.
Oh, and you said specifically slant asymptotes. You see them line rationals, but they're not all irrationals, right?
So you can have, I believe you can have a slant asymptote of a non-rational function.
Are we going to encounter that in this class? Okay.
Right, which is why we have that weird definition here. Because it doesn't necessarily have to be a rational function, right? So polynomial long division wouldn't work in that case. Right? The curvilinear asymptotes would also involve limits. Unless you're dealing with a rational function, that's just long division would be the easiest option. But there's a lot of types of asymptotes. In general, if your function behaves any kind of way on the ends, that would be an asymptote. With vertical asymptotes, right, we said that it could never intersect or never cross the asymptote, right? But it could actually meet it on one end. What about horizontal? Can we intersect a horizontal asymptote? Is there a limit to how many times?
Well, do you mean just go from having a line on one side of the asymptote to the other? Because I'm pretty sure we can do that.
So intersecting it and crossing. So it can intersect, it can cross. Is there a limit to how many times it can?
I think that depends on function.
So I'm just talking about in general.
No.
You could theoretically cross the horizontal asymptote an infinite number of times.
It's not a tan function.
Tan function never crosses. Or no, tan function never doesn't have a horizontal
Or,
asymptote.
oh, no, what, no, there's a function I'm thinking of. What's the one that, goes to hui, and then a hui, and then a hui, I believe that's a scientific term.
Those are really cool math terms. I'm not familiar with that function. Off the top of my head.
I think we have a crossover in that.
No, I got it, I got it. Yes, I was like, I know this is a thing. Oh, no, I know what it is. It's the inverse of sine and cosine, that's what I was thinking of.
I'm actually not familiar with the graphs of the inverse trig functions. I never really looked at them. I'll have to look at them.
Oh, actually, no, it's simply a secant. Look, this thing.
Well, they wouldn't have horizontal asymptotes.
No?
That doesn't have any horizontal asymptote.
There's a space in the middle it doesn't go to.
True, but take the limit as x goes to infinity of the inverse secant. Is that a number?
Okay, well, now hold on a second.
The answer is no. The secant's actually not ever leveling out. The inverse secant's never leveling out. That's the graph of the inverse secant. That graph doesn't level out on either end. So there wouldn't be a horizontal asymptote. There are values that it doesn't cross.
Yeah.
That I agree with. But that doesn't make it a horizontal asymptote.
Fair.
Right? Sine, cosine would never cross +1, right? Is that a horizontal asymptote? It's not.
All right, okay, I get it.
Right, so here would be a case of a function crossing its horizontal asymptote multiple times. Because remember, all we're concerned with is that it eventually levels out, which this one does. Right, think back to when we looked at, what was it, x sine of 1 over x? Remember how that behaved in the middle? So think of that behavior in the middle for this function. It would cross it an infinite number of times. Which means when graphing, you have to be careful. You have to check if it crosses the horizontal line, if it does, where and how many times. But who says that the function has to actually converge to some value? It could just keep increasing without bound, right? X squared. As x gets larger, so does x squared, right? So x squared would increase without bound. So the function has an infinite limit at infinity. Something's going to open. If f of x becomes arbitrarily large, for x being sufficiently large. And then we write the limit as x approaches infinity of f of x equals infinity. Similarly, for a negative infinite limit at infinity. So if your function's decreasing without bound, so your x becomes or your f of x becomes arbitrarily large in the negative direction as x becomes sufficiently large. That would be a negative infinite limit at infinity. And you'd write the limit as x approaches infinity of f of x is negative infinity. And there are similar definitions for x approaching minus infinity. Can we have one-sided limits at infinity?
I think so.
You say, did you say you don't think so, or you do?
Yeah.
You do? Which side? That's what I'm asking. So you think you have both sides?
Well, if it's on both sides, then it's going to be one side, right?
Well, you still have one-sided limits, right? Remember, there are two one-sided limits.
Yeah.
The limit exists if both one-sided limits are the same.
I'm sorry, what are you asking?
So you said you think there are one-sided limits at infinity, so I'm asking which side.
I suddenly want to retract my statement.
Can we approach infinity from the right? No, that would mean you're larger than infinity, which defeats the purpose of x approaching infinity. It means x is increasing without bound. That is technically always a left limit. And same argument for negative infinity, right? You can't really approach it from the left. That just doesn't make sense. So that would technically always be a right-handed limit.
So you can approach it this way, but not this way.
So we kind of ignore the concept of one-sided limits when we're talking about ad infinity and ad negative infinity. But now with an idea at least of what a limit at infinity is, let's formally define it. This definition is known as an epsilon n definition, and this will come up again in Calc 2. Say a function f has a limit at infinity if there exists a real number L such that for all epsilon greater than 0, there exists an n greater than 0, such that the absolute value of f of x minus L is less than epsilon for all x greater than n. And that's the idea. You have an epsilon band centered at L. L is your limit. If you can find a point N such that your f of x falls within that epsilon band beyond N. And this can always be true, so as you slide your epsilon band, you make it smaller and smaller, you can still find an N, right? So your N's also going to slide over. Same kind of idea, limit at negative infinity, except now N is going to be less than 0, and it'll be for all x less than N. And I will tell you, we're not going to do any epsilon N proofs. Now for the infinite limit at infinity. F has an infinite limit at infinity if for all m greater than 0 there exists an n greater than 0 such that f of x is greater than m for all x greater than n. So it just combines the definitions, the epsilon n definition that we just looked at, and the definition for an infinite limit that we looked at previously. Again, all it's saying is that f of x is increasing without bound. And then similar for negative infinite limit at infinity and limits as x approaches negative infinity. And for the negative infinite limit, it would just be m is now less than 0. That's the only difference. And then f of x would be less than m. Evaluating limits at infinity. When dealing with rational functions, or even a power function over a power function, the method is fairly straightforward. Look here. Factor out the highest power. So in this case, factoring an x out in the denominator. Move that x up to the numerator to become x to the minus 1 and distribute. And so what we're doing is this. What happens to 1 over x as x increases without bound? What about 5 over x? Those terms will just drop out to 0. As x increases without bound, what does 1 do? Stays at 1. So that's our limit. What's that limit? So there's our limit.
I think I remember what the summer problem, just if it's the facts of approach infinity, you just see what the higher power is, and if it's in the numerator, then assume that it approaches infinity, and if it's in the denominator, assume that it approaches 0. I'm guessing you want us to just write it out like
That's the examination of it.
Yeah.
This is the algebraic way of doing it. And it's not just for powers either. If you know how functions behave, they're very easy.
So I'm saying, like, if I were to just do that as my work, that.
You better hope it runs.
I mean, would you accept that as a work?
Well, it's not his work. And so if you just put infinity down there because of that analysis, and you're right, I'm happy. But if you're wrong, you've shown it work.
Yeah.
So that's all for credit. By the way, if you plug in infinity, what would you get? Is that one? Infinity over infinity is indeterminate. There's that indeterminate form. Now we're going to start seeing the indeterminate forms involving infinities. Highest power denominator is x squared, so factor out an x squared. Move it up to the numerator. So as x gets large in the negative direction, what's going to happen to 1 over x squared?
It's gonna approach 0, right?
They will both approach 0. So 5 over x squared will also go to 0. What about 1?
Well, that's just 1.
This is kind of like that limit. What's that limit? That limit's minus infinity. Here's a example on how you can see that. it's gonna hit really close to home. Get out of college. You have $400,000 in student loans. You make a $10 payment. Did your loan even notice it? No. That's why it's minus infinity. That's why it's minus infinity. Because you take a really large negative number, add 2 to it. Doesn't even freaking notice. No. Right, so again, it's like you have $400,000 in debt, you pay $2. Did you really move your debt anywhere? No. In fact, once the interest accumulates, your principal is now a lot higher. We'll continue with this on Monday. Have a good weekend.